Excellent, Mike. So can everybody see the PowerPoint? Good. I'm going to scroll it over to where we ended last time because I didn't feel comfortable sending in asking you guys to do proofs when I hadn't covered it totally in class. I was trying to rush, and so I postponed our quiz till Wednesday so that we can actually look at an example of what I expect and where all the points are going to be allocated or how I grade. And some of you sent me your homework. I'm perfectly happy to look at it. I'm not collecting it for grade, but I'm perfectly okay with looking at it beforehand to see how you did. So you're getting dizzy here watching this. So I believe I did this proof. Is that correct? I did the proof of the unique element. Okay, so let me now move to I gave you the homework. Did I do this one where the abelian? Oh, okay, Ray. Okay, so hey, chatting online actually helps me as a skill now. That actually helps me do other things. Imagine that. Dan, can you hear me? Because I noticed there's not a speaker on yours. Okay, I guess he might answer when he sees the chat. So in this problem, I wanted to go over some examples and show you how kind of I structure the proofs so that it's clear. This is number 32 on page 48, and the statement is if G is a group with identity E and x times x equals E for all x and G, then G has to be abelian. So what we know, that's the first step, is to write down everything you know, and the know is the material with between the if and the then statement. So we know G is a group. Because it's a group, it has an identity, it has inverses, and it's associative. So those three nuggets of information I have that I know. Okay, second step is to also, I always thumb through the book. Now, people learn these kind of things differently. I had a friend who would take the German girl that helped me with proofs. She would write everything down beforehand, study it carefully, and then go to the homework. I guess my approach was start with the homework and then flip through the book and then write down the information that I would need to solve the homework. Either way, we ended up learning about the same amount. So however you would like to do it, read carefully through the book first and go through everything we've done in class and then take good notes and then go to the homework, or go to the homework first and then start flipping through the book. So using the Thomas approach, I go through the book and I see what could be relevant. I noticed that on page 41 we have something called the cancellation law that basically says that I can cancel. I'm hitting both sides with an inverse. And so I write that down as a potential nugget of information that I could use. And I also know from the given, I underlined it up there, that x star x is equal to E for every x in G. So far, is everyone good? No questions? All right. So now I have to show G is abelian. So I didn't cover the definition of abelian. Abelian is just it's named for Abel, who's they have a little biography of Abel inside the book, which is nice. But it really just means that the group is commutative. So A star B is B star A for all A and B and G. Okay. So now it's time to play. Preferably you'd have all your know in front of you and your show in front of you, and you'd just start to assemble so that the know leads to the show. But I'm just going to play around. Why would I start my play like this, AB star AB, and write down what it's, or BA, and write down what it's equal to? Well, I would start doing that because I know that my end result has to be something like AB is equal to BA. So, and I know that, I also know that something about squaring elements, that B star B turns out to be B, for example. So that's what made me think of taking AB and starring it with BA. All right. So why try this? Because I want to involve A, B, and BA in some kind of equation, and my end goal is to get AB equals BA, so that's why I did this. And I also had the property that I know something about squaring elements. So I need to apply my know because this is a textbook problem and they wouldn't give me something unless I have to use it. So the book is not hard enough yet. There are books where they actually try to trick you, but here they're not trying to trick you. So the first chess move that I have is to remove the inner two parentheses, which I'm allowed to do by the associative law. That gives me AE equals A. Why? Because I'm using the know. And notice that I just copied and pasted the know. Preferably when you're working at your desk, you would have these pieces out in front of you. Or when you have a piece of paper, you would have these pieces out in front of you. Next, I use the property that E is the identity, so it leaves things unchanged. And so I get A star A, which turns out to be E. Again, by the know. I'm applying the know here as well. So what does this give me? Well, it tells me that the inverse of BA is AB, is BA, the inverse of AB is BA. So remember when I presented last week, I asked you not to use the inverse symbol, and then as I was actually working proofs, I realized there's no way around using the inverse symbol. I have to use it. So what that tells me is that I have an inverse, and since the inverse is unique, I know that this is the only possible inverse. So it tells me something. So this is what I mean by play. I had an interesting story told to me by a physicist who left the field of physics in academia because he said that it would take him 4 hours to write a proof and everybody else seemed to get it quickly. But that's not true. Everybody probably lied to him and told him they got it quickly. The truth is, you spend some time playing around like this, and it's pleasurable. It's fun. You're solving a puzzle. So this is my nugget of information that I got from my first little play around. Okay, so I'm going to play some more. I also know that AB star AB is E because if X is AB, then by applying the no here for AB star AB, I get AB squared is also E. Well, isn't that nice? So AB inverse is also AB. Well, I'm done. Can anybody put in the chat box why I'm done? I'm not done, like fed up done, but I'm done with this proof. Can you see the last line of the proof now? Right, exactly. Inverses are unique. Because inverses are unique, I'm done. You don't need more than one way to skin a cat. So you don't need to go the way I did. This is the way I played and got to it. So there are other ways to do things, and you could have certainly done it the other way. So my play led me to this. So that's my last line by theorem 4.17. Jeff, why does ABAB equal BAAB? I'm missing BAAB. Well, you'd have to take some steps to show that. If somebody has to ask you why why something is true, I mean, you would go through the same steps, right? You'd have to show BAAB is equal to BAAB, which by the associative law, and then you'd have to show that you get So I don't believe that these are less steps. These are exactly the same steps. So you'd use a different approach to get there. But you do have to show the details. If you're not applying the fact that you have a group, I had a really great professor that used to ask questions like, if I relax the condition of being in a group, is this still true? And I would come in with these polished proofs ready to present to him, and he would ask me this one question. He was a great professor, although at the time I didn't particularly care for this line of questioning. So always look around and ask yourself, have I used the fact that I'm working on a group anywhere? If I haven't used that fact anywhere, I've not put enough detail because it was in my hypothesis. Thumbs up? We didn't have to show it was unique. I used the uniqueness of the inverse to say that I'm done. I didn't quite kind of do my last. So here is my last thing. You see these AB over here is highlight and the BA over here is highlight. Because the inverse can't be two different things, then these two things on the right side must be equal. And that was what I wanted to show. If I can't have it, the slide, I could scroll back to that slide where we wrote down what we have to show. And what we had to show was that AB is BA. No, I mean, you could. I don't think that that's too much detail. You could still say, I know that let A. So I think on the next page I have the clean write-up. So what I was showing you was the scratch write-up of how do I get my pieces put together, how do I get the null and show. Let's look at the clean write-up with all the details written out. So in this case, I have to show that G is a group, it's got an identity, X star X is equal to E for all X, and I have to show that G is abelian. So here's the proof. First, observe that AB star AB is equal to E by applying the hypothesis with X equal AB. So I just go through the steps. So I'm just going through the steps, but explaining every step of the way. And let me continue on. That since AB equals E, then AB inverse is AB, but we also have AB, BA is E, so AB inverse is equal to BA. By theorem 4.7, inverses are unique, so AB inverse is AB, which is BA. So it has the punchline written there. This proves that AB is BA for any element A, and B, and G, and this concludes our proof. So you don't have to show that A star B is in G, but if you want to put in that extra line that if I take an arbitrary A and an arbitrary B in G, then by closure property, A star B has to be in G. So A star B also follows all the rules of being in the group. It's fine to put that in there. Paul, does that answer your question? Okay, good. So I wanted to also, I don't know if I blasted through this, but I wanted to show you how questions are asked on quizzes. And I'm not sure if it went out of order here. Okay, there it is. So what I do is I ask a question. I think it's hard to see on my little screen here, but you can look at it on the PowerPoint. This came from number theory last semester. And there's a rubric on the side that's looking for whether you wrote down the hypothesis. That's just slicing between the if and the then and splicing it down. And if you expanded the hypothesis, that is the next sheet that I had where I said, okay, what do I have? I have that it's group. What does that mean? It means that I have these properties. What about my hypothesis? It means this. So I write all those things down. And then I write down the conclusion, what is meant by the show. And then I expand out what that means. The conclusion was that G was abelian. What does that mean? It means that AB is BA for every element A and B in the group. So that's what I mean by expanding. And so the bulk of the points comes from just piecing together those pieces of information. I don't expect all the time everyone to have a great hair day and be able to get the entire proof on a quiz. So there's only 5 points for logically step-by-step putting the proof together. That may happen, that may not happen. I do give partial points for having a good trying to put things together and having the right direction, or if I feel like they're, with a cup of coffee and a little bit more time, you would have got it. I'm pretty generous there. So that's how I grade. So it's pretty structured. Are there any questions about how this will be done? One thing to caution you about, everybody usually does well on like when it's structured like this, everybody slowly starts to get the hang of it, how to put things together. But once in a while I have a student who wants to bypass doing the know and the show and actually listing things out, and they go straight to the logical step by step. And so their whole pages are full of scratch. And if they didn't actually put the proof together, which oftentimes they can't, that does end up with nothing for me to put down for the rubric, because the points are allocated on having the pieces in place. And so even though they might have a lot of writing and scratch work all over the place, it ends up being nothing. So that's a danger to watch for. So I would get in the habit of putting, this is what I know, this is what I have to show, and putting at least what information you have there to start out with. Okay, if there's no questions, I did have a couple more examples here, and I did leave at the end a definition, a formal definition of a braid group. So if you're interested in looking at that, it has a little bit to do with topology. So only if you're interested in what the formal definition would be, go ahead and take a look at that. And then I also have in here the properties of a Rubik's Cube. I had mentioned to you earlier that the Rubik's Cube itself forms a group, and the actions are just like the dihedral group. You have R01 would be the rotation of face 1. R11 would be rotate right once, 90 degrees, rotate twice, rotate 3 times. And in a way, it's actually more simple than the dihedral group because you don't have any symmetries. You can only rotate faces. Of course, it's quite big. And if you look online, you can find the entire Rubik's Cube group that's formed. Now, being in the Rubik's Cube solution is the identity, and you really are proving, once abstract algebra tells you that it has a solution because of the cancellation law. So that's what's nice about it. And it's kind of neat. Okay, any questions before I move on? Dan, you mean the Rubik's Cube? No, not really, because it doesn't have a symmetry across reflections. It only has rotations. There's actually a whole set of games and algebra of games. A friend of mine who used to teach at Montclair and now is working for the American Math Society, he used to work on flip shift games. There was another game I saw recently at the MAA, but they all have to do with these properties of groups. So it's not the total dihedral group that you get. You can usually rotate. Sometimes in these like these flip shift games, I don't know if you've ever seen these numbers in a row with a space, and then you can move around the numbers. You don't quite have a symmetry. You have a flipping and shifting action, but they form a group as well. And so you can start looking at the algebraic structure of these groups, and it's fun stuff. I don't know if you guys know Jimmy Johnston. Jimmy Johnston is one of our graduate students right now, and his thesis is actually on one of these games. It's on the Rubik's slide game. Okay, away from fun stuff, like Rubik's Cubes, and I'll move to the new stuff, which is fun too.